In this video, we'll talk about continuous functions as a whole. So we say that a function is continuous if it's continuous at every point in its domain. And there are a lot of things that we know based on our previous discussions. We know that polynomials are continuous functions, because at every point of the domain, we have the substitution method property, and the domain is everything, so we're great. Rational functions are also continuous, because everywhere they are defined, they are continuous. The only issue is where the bottom is 0, but at those points, the function is not defined. Algebraic functions also have this property, so anything like square roots, weird powers, those also work. Really, a lot of things are continuous, which is great. Now, the main change of discussion here is now we're talking about the function itself as a whole being continuous and not just the value at a point. This continuous function is a type of object that has this nice property where the substitution principle applies at every point of its domain. What we want to think about here is if I have continuous functions, are there things I can do with these functions that are better or nicer because they are continuous? So what can we do with continuous functions? Well, the main thing we'll see is that continuity means it plays nice with limits, right? The fact that limit x goes to c of f of x equals f of c really means that I can sort of pass the limit through the function itself. But I can really think about this as I'm taking limit x goes to c of f of x, and because f is continuous, I can put the limit inside the function operation here. This is f of limit x goes to c of x, which is just f of c. So the function playing nice with limits is really what we're going with here. A function is continuous if it behaves nicely around these limiting operations. So what about combining these functions? If I know things are continuous, can I combine them together to get more things that are continuous? The answer there is yes, thankfully I can. And all of this really comes back to our limit laws and the fact that limits behave nicely under certain circumstances. So what happens here is if I have f and g that are continuous, then we know f plus g is continuous. And why is that? Well, let's break that down in terms of limits. So if this were to be continuous, I would want that limit as x goes to c of the function f plus g of x to equal f plus g plugging in c. But this here is the same as the limit as x goes to c of f of x plus g of x. And I know that by my limit laws, I can split up that fx plus g of x into two separate limits. Once I have that, I know f and g are both continuous. So this is just f of c plus g of c, but that's the exact same thing as f plus g of c. So we're using the fact that these functions are continuous, f and g are continuous, that gets us this step here, and our limit laws gets us from here to here. So limit laws plus assumptions on continuous functions give us this result. Similarly, f minus g is also continuous with the exact same property. F times g is continuous. F over g is continuous. This doesn't need a condition on it because if g is 0, we're not in the domain, so the function is not defined. Therefore, it's still continuous where it's defined, it's just not defined at that point. F to a power is continuous, the nth root of f is continuous, all by the same logic of our limit laws from before. And we have one more result from this. I'll put separately because more involved. If f is continuous at c and g is continuous at f of c, then the composition is continuous at c. This basically comes down to being able to move limits through the function operation as a part of continuity. So if f is continuous at c and g is continuous at the point where f would map to, then this composition here is continuous at c because f is seeing c, it's nice. G is seeing f of c, also nice. Therefore, this all works out. So there's the idea of continuous functions as an entire object, and what we can do with continuous functions to combine them to make smaller continuous functions into more involved and more complicated ones, and still know that we can use substitution principle to evaluate limits in this way.